This video is a summary of the infinite square well. We're gonna do 3 examples in this video, but before that let's review a few things. Let's review the potential of the infinite square well is made out of 0 inside the well, so this is when x is between 0 and a, and this infinity everywhere else. So if I want to plot it, if I want to plot this potential, this is 0, this is a, this is in one dimension, everywhere else is infinite, and inside the well we have no potential function. And if you remember the solutions for this, we have the ground state solution, looks something like that, and then we have the first state is something like that with one node, and so forth. Okay, so we have arrived using Fourier trick. Okay, we have arrived to the final solution x psi of x comma t is equal to sum of all the states starting from 1 to infinity of some constant c of n times the square root of 2 divided by a times the sine of n pi divided by a times x times the time part of this equation, which is e to the minus I times n square pi square h pi square h bar divided by 2 mass times the width of the well square times t. And here we have the energy values. E sub n is made of n square pi square h bar square divided by 2m a square. One more thing, let's look at this c sub n. Again, we can use Fourier trick to find c sub n equals to the square root of 2 divided by a times the integral from 0 to a times sine of n pi divided by a times x. Let's put brackets here, times psi of x comma 0 dx. So that does it. Given the initial wave function psi x comma 0, we first compute the expansion coefficient c sub n using this equation, okay, and then plug these equations into the result into the equation from the previous slide. So now let's look at the first example of this summary of the infinite square well. Let's solve the time-independent Schrödinger equation for the centered infinite square well. So the centered infinite square well looks something like that. It's infinite, I mean, between minus a, and it's 0 everywhere else. So I'm sorry, it's infinite everywhere else, it's 0 inside. So this is our potential function v of x. This is x. Alright, so this is almost identical to the one we did earlier in video number 8, but here the boundary conditions are different. Here the boundary conditions tell us that psi of a must equal to psi of minus a, and they both equal to 0. So let's look at the solution for this. If you remember the solution from video number 8, the solution is psi of x is equal to a times sine of kx plus b times cosine of kx. Put a line here. So looking at the boundary conditions, we have a times sine of ka plus b cosine of ka is equal to 0. Also we have minus a times sine of ka is equal to b times cosine of ka equal to 0. So let's call this equation number 1, and this is equation number 2. So now let's subtract equation number 1 from number 2. So what do we get? We get, so this is subtract a times sine of kx, I mean ka is equal to 0, and from here we get ka is equal to j times pi, or a equal to 0, right? And if we add the two equations, we get b cosine of ka is equal to 0, which tells us that ka is equal to j minus 1/2 times pi, or b equal to 0, where j runs from 1, 2, 3, and so forth. Alright, so if b is equal to 0, then a cannot be equal to 0. So this is, so a cannot equal to 0. And this tells us that k must equal to j times pi divided by a. In this case, if we let in, so let n equal to 2 times j, so n is always an even integer, right? Then k is equal to n times pi divided by 2a, which tells us that psi, in this case, psi of x is equal to a times sine of n pi x divided by 2 times a. Let's go ahead and normalize this, because we can. So 1 is equal to a squared times the integral from minus a to positive a times sine squared of n times pi times x divided by 2a dx. So this is equal to module square of a times divided by 2. This is equal to 1, which tells us that a is equal to 1 divided by square root of 2. Oh no, I'm sorry, it's equal to square root of 2. So finally, so this is done for the first case. The second case, if a is 0, then b cannot equal to 0. In this case, we get psi equal to b times cosine of n pi times x divided by 2a. If we normalize psi, we get 1 equals module square of b times the integral from negative a to positive a of cosine square of n times pi times x divided by 2a, which is equal to module square of a times b, which is equal to square root of 2, equal to 1. Therefore b now is equal to the square root of 2. Alright, in both cases, the equation we worked on earlier, which is the Schrödinger equation, right, for the infinite square wheel, tells us that the second derivative of psi with respect to x is equal to minus k square times psi, where k is as usual defined to be 2 times m times e over h bar. So in either case, this equation gives us the allowed energy values, which what we are looking for, to be h bar square times k square divided by 2m. So let's put k back into here. So the allowed energy values equal to n square pi square times h bar square divided by 2 times m times 2a square. And it agrees with video number 8. If we substitute x for x plus a divided by 2, we have the solution becomes to be a square root of 2 divided by a times the sine of n times pi divided by a times x plus a over 2, which is equal to the square root of 2 divided by a times sine of n times pi times x divided by 2a plus n times pi divided by 2, which is the same as, so this is psi minus 1 to the n power times the square root of 2 divided by a times the sine of n pi x divided by 2a. This is if n is even. Then we have minus 1 to the n minus 1 divided by 2 times the square root of 2 divided by a times cosine of n times pi times x divided by 2a. This is if n is odd. There you have it. So this is the solution for the psi with the allowed energy in the previous slide. If we plot the solution, the psi, for within the potential v of x, we get the first solution. This is n equals 1. It's a cosine function, so it looks like this. So this is the solution, cosine of n times pi, x divided by 2a. So this is n equals 1. So n equals 2. It's even, so we have the sine, x and v of x, just a sine wave. This is centered. So this is sine of 2 pi times x over 2a. Of course, this is here, it's minus a, and here is positive a. So actually this doesn't exist. And this is here minus a, and here is positive a. Let's do one more where n is equal to 3. So n equals to 3. We have our potential function v of x. I mean, no, psi of x, my bad. So this is cosine of 3 times pi times x divided by 2a. So here we have minus a, have positive a, and it goes something like that. Let's look at a particle in the infinite square well with the initial wave function psi of x and 0 equals to a times sine cube of pi x over a. This is if x between a and positive a. So if we look at the potential, this is our potential, this is 0, this is a, it's infinite everywhere else, and the potential is 0 in the middle. But we start with the initial wave function equals to that. So in this question we're gonna find a, the normalization constant. We're gonna find the wave function that depends both on position and time, and also we're gonna look at the expectation value of x. So let's remind ourselves of some trig identity. That's the sine of 3 theta equals to 3 sine theta minus 4 sine cubed of theta. Let's go ahead and use this identity to find a. If you remember from video number 8, we have the solution for the infinite square well. Psi of sub n of x equals to square root of 2 divided by a times the sine of n pi times divided by a times x. But now we have a linear combination of both because we have initial wave function. So now the solution is psi of x comma 0. It's a linear combination of both. It's the normalization constant a times the square root of 2 over a times 3 over 4 psi 1 of x minus 1 over 4 psi 3 of x. So normalizing this, we get a squared times a over 2 times 9 over 16 plus 1 over 16. Which gives us, this has to be equal to 1, right? So it gives us a equals to 4 divided by square root of 5a. Alright, so now psi x comma 0 is equal to 1 divided by square root of 10 times 3 psi 1 minus psi 3. Now if we invoke the time dependent in the wave function, we get psi of x comma time equals to 1 divided by square root of 10 times 3 psi 1 times e to the minus I energy 1 times time divided by h bar minus psi 3 times e to the minus I e sub 3 times time divided by h bar. So the expectation value for this is psi star psi is equal to 1 divided by 10 times 9 psi 1 square plus psi 3 square minus the cross terms, which is 6 times psi 1 times psi 3 times cosine of E2 E3 minus E1 divided by h bar times time. The expectation value of x is equal to the integral from 0 to a of x psi star psi, right, dx, which is equal to 9 over 10 times the expectation value of the first wave function plus 1 over 10 times the expectation value of the second wave function minus 3 over 5 times the cross terms, which is cosine of E3 minus E1 divided by h bar times time times the integral from 0 to a of x times psi 1 psi 3 dx, where if you're wondering what is this expectation value of the first wave function, the expectation value of x at the nth state is always equal to a over 2. So this is the expectation value of x in the nth stationary state. The remaining integral, we have 2 divided by a times the integral from 0 to a times x sine of pi x over a times sine of 3 pi times x divided by a dx. Now the trig identity that I introduced earlier comes handy. So now we have the remaining integral equals to 1 divided by a of times the integral from 0 to a of x times cosine of 2 pi x divided by a minus cosine of 4 pi x divided by a. Dx. Carry on, we get 1 divided by a times a divided by 2 pi square times cosine of pi 2 times pi times x divided by a plus x times a divided by 2 pi times the sine of 2 pi x over a minus a divided by 4 pi square times cosine of 4 pi x divided by a minus x times a divided by 4 pi times the sine of 4 pi x divided by a, and this is being evaluated from 0 to a, and if you do the evaluation you get what? You get 0. Alright, so now we can put everything together to find that the expectation value of x is equal to 9 over 10 times a over 2 plus 1 over 10 times a over 2, which is equal to a divided by 2. Let's look at the third example of the infinite square well. We have a particle of mass m which is in the ground state of the infinite square well. Suddenly the well expands to twice its original size, leaving the wave function undisturbed. Then the energy is measured. First we're gonna find what is the most probable result, and then we're gonna find what is the next most probable result, and then we're gonna find the expectation value of the energy. Let's remind ourselves of the potential of the infinite square well. So it looks something like that. This is x. It's infinite everywhere else, and it's 0 between 0 and a. This is v of x. So now all of a sudden this well expands from 0 to a, and it went from 0 to 2a. So the ground state energy, if you remember, it looked something like that, right? And now the ground state energy after the expansion looks something like that. So first let's find the most probable results. Let's look at the new allowed energies. E sub n equals, if you want to review, this is all in video number 8, n square pi square h bar square divided by 2m, and it used to be a square, but now we have 2a square, so we're gonna put 2a square. And the wave function psi of x comma 0, if you recall, is equal to the square root of 2 divided by a times the sine of pi over a times x. And the nth state of the wave function is equal to the square root of 2 divided by 2a times the sine of n pi divided by 2a times x. Alright, so now let's look at the coefficients c sub n. So c sub n, if you remember from Fourier transform, we have square root of 2 divided by a times the integral from 0 to a times the sine of pi over ax times the sine of n pi over 2ax dx. So evaluating this integral, simplifying this integral, we get square root of 2 over a over 2a times the integral from 0 to a times cosine. Remember sine, we can write them in terms of cosine minus cosine, trig identities, n divided by 2 minus 1 times pi x over a. I mean over a. And this is minus cosine of n over 2 plus 1 times n x over a, pi x over a dx, which is equal to 1 divided by square root of 2a times the sine of n over 2 minus 1 times pi x over a divided by n over 2 minus 1 times pi over a, right? Minus the sine, basically the same thing, of n over 2 plus 1 times pi divided by n over 2 plus 1. No, sorry, this is pi x over a, yeah. And here we have pi over a. And this is, we're gonna evaluate this from 0 to a. If you look here, you'll notice that n cannot be equal to 2, because this will give us 0 here. I mean, this one here will give us 0, so n cannot equal to 2. Alright, so carry on. We get, after a lot of algebra, I recommend you do this. We get 4 times square root of 2 divided by pi times the sine of n over 2 plus 1 times pi divided by n squared minus 4. So this is equal to 0 if n is even, and it's equal to plus or minus 4 times square root of 2 divided by pi times n squared minus 4. This is for odd n, if n is odd. So this is c sub n, right? So this is basically everything, but we didn't evaluate c sub 2 because we couldn't, right? So this is square root of 2 divided by a times the integral from 0 to a times sine square of pi divided by a times x dx, which is equal to square root of 2 divided by a times the integral from 0 to a times of 1/2 dx, which is equal to 1 divided by square root of 2. This is for n equals 2. So now the probability p sub n is equal to c sub n times c sub n star, right? So we have c sub n module square, which is equal to 1/2. This is n equals 2, 32 divided by pi square times n square minus 4 square. This is, n is odd, and we have 0 if n is even. Alright, so now the most probable, if you look at here, the most probable is the second state, e sub 2, because it's 1/2. So basically, if you look at this, when the wave function is in the second quantum state, it's equivalent to to all of the other quantum states combined. This what this thing means. So now we have e sub 2, this is the most probable, so this is part A finally, which is equal to pi square h square divided by 2m times a square. And with the probability of 1/2 p sub 2 equals 1/2. The next most probable, this is part B, is e sub 1, which is equal to pi square h bar square divided by 8m a square, with the probability p sub 1 of 32 divided by 9 pi square, which is equal to 0.36025. Alright, so now part C, if we want to find the expectation value of the energy, so this is expectation value of the Hamiltonian, which is equal to the integral of psi star times h times psi dx, which is equal to 2 divided by a, because we have two psi's, right? That's the integral from 0 to a of sine pi over a times x times the Hamiltonian, which is h bar squared divided by 2m times the second derivative. That's why it's very important you stick the h between, not in the front, because in the front you're gonna have the product rule, you're gonna get the wrong results. So this is the Hamiltonian. Remember, the potential is equal to 0, so we don't have the potential term, times pi over a times x dx. But if you look at this, this is exactly the same as before the wall moved, and we know the answer for this integral from video number 8. The answer for this integral equals to, you can do it by hand, but we want to save time here, is equal to, so this is expectation value of h, pi square h bar square divided by 2 m a square. There you have it.